Okay, so you might be interested in comparing whether or not two variables are correlated with one another. And there's just a little image here depicting a strong linear correlation using a scatter plot. But we're going to go over the two most common correlation tests, the Pearson correlation and the Spearman correlation. We're going to focus first on the Pearson, but we need to do this first. Again, like you've seen throughout all the slides for this course, one of the most important things to deal with is the normality test. So again, you need to be able to do a normality test on the data. Depending upon what you're testing, there are normal statistical tests and there are nonparametric ones. So we have a Pearson correlation and we have Spearman rank order correlations for data that are skewed or nonparametric. So environmental data are often not normally distributed. So that's the case for a lot of health data. So you'll see Pearson correlation used a lot, often inappropriately. Normal data suggests the mean, median, and mode are similar, but non-parametric data might be bimodal or skewed. Health data, that happens a lot. Income data, non-parametric is common, as you know. So correlation data or correlation tests should be appropriate. So non-parametric should be used. Parametric should be used when it's normally distributed. For testing for normality, there's a variety of different types. For small data sets and for data that's less than like 2,000 observations in Stata, the simple command swilk for the Shapiro-Wilk test is usually good enough. For huge data sets or large, getting over 2,000 to 4,000 more observations, Shapiro-Francie is usually good. All right. Again, if you have a high p-value from a normality test, p is equal to 0.452. That's above 0.05. Some people even use a cut point of 0.2. If you've got a high p-value, definitely anything over 0.05, you could, for this class, you could say the data are normal. Low p-values below 0.05 suggest that there's a statistically significant difference. So low p-values below 0.05, you know for sure there is a statistically significant difference between normal and not normal. So if there's a significant difference from normality, if it's significantly different than normal, then you should conclude that it's not normal. And if you do that, then there's an appropriate statistical test for correlation for that. So again, in order to do the normality test, the data must be in columns. And in order to test for correlations, we want the data also to be in columns. So you may be interested in seeing if variable X is correlated with something like variable Y. Things like, is there a relationship between exposure to disinfection byproducts and drinking water? You know, the chemical reaction of chlorine causes cancer-causing compounds. We know some water plants in the United States are more frequent to violate that. And you may also know the stomach cancer frequency for that county over the last 20 years might be 1 in 100,000, 5 in 100,000. You know, you can compare number of violations with stomach cancer frequency and see, is there a correlation? Or maybe, is there a correlation between the number of cars on a highway and fine particulate matters, the pollution in the adjacent community? So you might be interested in seeing, maybe you've got a difficult way of measuring manganese dust inhalation on workers. And there's a new monitor that was developed to do the same thing that's not so big and bulky. And you might want to compare, is there a correlation between these two methods? You could have done a paired t-test or a sign rank Mann-Whitney type test, but those may not be necessary. You could do a correlation instead. The correlation test is very simple. You may also be interested in maybe looking at county level auto fatality rates and the percent rural. So when you got two continuous variables that you want to compare, correlation test is pretty good. Maybe you want to see the E. coli levels measured with a one method correlate with E. coli levels measured using a more difficult method. It's important to remember, though, that correlation is not causation. Just because something is correlated does not mean it causes it. For example, if somebody buys an umbrella, it doesn't mean that it's going to cause it to rain. And if you were to look at the amount of umbrellas sold in the United States, you'll find that as umbrella sales go up, the likelihood that it rained that day goes up. It does not mean that the umbrellas caused it to rain, and nor does so. Another one, we can look at like Major League Baseball player salaries. You can see that they've been, for the most part, steadily increasing. The league minimum salary has been pretty low, but the top paid folks have been making more and more and more every year. This is from 1989 to 2014. So as baseball salaries go up, so does the year. So year is correlated to some degree with the salaries. So year and these dollars are, you can see a relationship. Something looks like it's going up. This is an image that was from this group called Autism Speaks. They are providing information that suggests that the autism levels are rising, and that's true. They do put this from the CDC, that the numbers that they put in their graph were from the CDC. So the frequency of autism has been increasing. It's also correlated to some degree with year. As you go through time, it's getting higher and higher. Now, we can plot the autism rate here from this image with the Major League Baseball player salaries. And we pick the 50th highest paid baseball player in millions. So the one that's the 50th, the green line. Using this green line, and you can see as you put the baseball salaries for that year with the autism rates for that year, you can see this strong correlation between the baseball player salary and the autism rate per 1,000. Now, I don't think that the baseball player salary is causing autism, but you can see there is a correlation. There is a statistical correlation, and we can test that statistical correlation to see how strong that correlation is. All right. You can see that the autism rate per 1,000 is correlated with year. This doesn't look like that graph because this actually looks more like a linear trend than exponential, but they put exponential on here. Maybe they've manipulated the data a little bit, but yeah, definitely a linear trend. The autism rates are going up. So there's a relationship or a correlation between year and autism, just as there's a correlation between Major League Baseball player salaries and autism. So again, correlation is not causation. In order to see if a correlation is present, you must have your data in two more columns, and the hypothesis test, similar to the odds ratio, except for where 1 is like on an odds ratio, no effect, less than 1 is like protective, more than 1 is harmful. Here you have 0. If the correlation coefficient is 0, then it's not it's not a correlation. There's no correlation, or it's weak. Nothing is there. Correlation coefficients can be negative. You can have an inverse relationship. Correlation coefficients can be positive. So if the correlation coefficient is equal to 0, that means nothing is going on. If the correlation coefficient is not equal to 0, so the 95% confidence interval around that correlation coefficient does not include 0, then the correlation coefficient is different than 0, and that suggests that there's a statistically significant effect. So again, the null hypothesis says there's nothing different than 0, nothing's going on. The alternate says yes, there is something going on. Correlation coefficients have p-values, so a high p-value indicates that we can't reject the null hypothesis, and we have to conclude that the correlation coefficients are, not different than 0. So high p-value, 0.241, it's greater than 0.05, something like that, you'd conclude that there's no statistically significant correlation. Regardless of what the correlation coefficient is, the p-value tells us whether it's significantly different from 0 or not. So again, there's two major correlation tests. If the data are normally distributed, so you do a Shapiro-Wilk test and the p-value is greater than 0.05, it's a really high p-value, maybe you can do the Pearson test. Every column that you're comparing should be normally distributed in order to do this test. If any one column does not meet the normal normality test, you should do a Spearman correlation test. So in Stata, there are a variety of correlation commands that you can use. You can use the Pearson correlation commands for variable 1 and variable 2. You can do core, variable 1, variable 2, variable 3, and so forth. These will not give you the p-values. You do pairwise correlation, or it's called PW core, and then your variables, and then put that comma significant behind it. It will give you the p-values. So if you want the p-values for Pearson correlations, do PW core, var1, var2, var3, var4, whatever, however many variables you want to use, comma, sig. For the non-parametric equivalent, you will use Spearman, and then the variables that you're wanting to see are correlated. If you use more than two variables, you will not be able to get the p-value. So if you do them two at a time, variable 1 versus variable 2, you'll get the p-value. So you'd have to do them two at a time. If you put all three variables or four variables or five variables or whatever you want to put in there behind Spearman, then it will not give you p-values, it'll just give you coefficients. And this may make a difference where it's auto-capitalize this on PowerPoint. A large S may not be good. You may want it to be all lowercase. I don't know. All right, so the correlation coefficient range again can go from -1 all the way to as high as +1. Correlation coefficients can't be less than -1. They cannot be more than 1. Again, these do have a 95% confidence interval. So you might have something with a correlation, see down here, a correlation of like 0.45. It shows like a moderate correlation, but if there's a lot of error around it, and the software doesn't report the error, but there's a lot of error around it, if this crosses 0, the 95% confidence interval, then we have insufficient evidence to conclude that this is, even though it's a moderate correlation, it's different than 0. The more data you have, the tighter these confidence intervals are, the more likely you're going to have a statistically significant result. Less data, you're going to have more error, more likely to have statistically insignificant results. Inabilities to detect differences. You might see in literature Pearson correlation coefficients called R. They can be squared into R squared. Spearman correlation coefficients are called rho, Greek letter rho. It might be like the Greek letter rho or be R sub S. A perfect positive correlation, 1.0, looks like this. Negative correlations go down. You hardly ever see these, especially in human collected or environmental data. So perfect correlation, 0.8, 0.4. Here's nothing going on. 0.4, negative 0.4, it's going down. Negative 0.8, it's going down. -1, perfect -1. You can look at those and have a good understanding of what they look like. So we're going to do some practical application here in a minute. So you want to see if your data are correlated. You want to look at autism rate per 1,000 versus the Major League Baseball salaries. So you have to know what you're comparing. You have to ask, are the data normally distributed? We do the p-value test from the Shapiro-Wilk. We see high p-values. They are statistically significant or statistically insignificant, no difference from normality, so they're normal. We use the pairwise correlation with the sig. We see a low p-value, 0.0006, so they are correlated. So this will be continued.